Okay, so we restart the session. Next talk is angular momentum evolution of young Roma stars and brown dwarfs, presented by Sean Matt. Yeah.
Okay, good. Sounds like you can hear me. This review was organized by Jérôme Bouvier, who's put together this nice, great group of expert theorists and observers, and then myself, to review the tremendous amount of progress that we've had since PP5 in understanding the angular momentum evolution of low-mass stars. So just in case you're not intrinsically convinced, I'll just mention really quickly a few things about why rotation is important for a lot of the research that's being done by everybody, I think, attending the conference. First of all, it's a fundamental, angular momentum is a fundamental property of stars next to mass and metallicity. And so we want to understand how it works and how it affects the internal structure and dynamics. And we know that that actually affects things we can observe on the surface, as well as rotation is important for driving magnetic activity, which I'll say a little more about on the next slide. The magnetic activity produces magnetic fields, high energy radiation, and winds, which is a primary way in which a star interacts with its environment, meaning it's surrounding accretion disk while it's forming, as well as planets and planetary systems. Also, as I will touch on throughout the talk, by studying the evolution of angular momentum, it's going to complement our already good knowledge of stellar evolution that we already have. It's going to complement that picture in a lot of interesting ways and relate to a lot more types of data than your classical stellar evolution does. So, low-mass stars are all magnetically active, and magnetic fields are extremely important for the angular momentum evolution of stars, for transmitting torques to and from the star. And so it's important to understand a few concepts related to their magnetic activity. The first is here, well-known relationship. If you plot the X-ray luminosity versus Rossby number, you see a very strong correlation where the Rossby number here, to remind you, is the rotation period divided by the convective turnover timescale. And this is a dimensionless number that's important for dynamo calculations. But what you see is the slowly rotating stars, which are the ones on the right here, have a magnetic activity that is correlated with the rotation rate of the star. But for fast rotators, and this is what we call a non-saturated regime, because for the fast rotators, you see the magnetic activity is no longer depends on the rotation rate. And here, this is referred to as the saturated regime of magnetic activity. It's a very clear relationship. Secondly, we already knew at PP5 from Zeeman broadening measurements and a number of indirect arguments that the magnetic fields of stars, both pre-main sequence and main sequence, are not always simple dipoles. In fact, they're characterized by complex fields. But due to advanced new instruments in spectropolarimetry, we now have detailed surface magnetic field maps of a number of stars, both on the main sequence, pre-main sequence, both accretors and non-accretors. And this just, again, brings home the point that the magnetic fields are often complex. So it's going to be important. So the rest of my talk is organized in 3 sections here. First, I'm going to just review the recent increases in the amount of observational data and what kind of trends we're going to see from that. Second, I'm going to talk about review the physical models for torques that explain and govern the angular momentum evolution of stars. And finally, talk about spin evolution models, which actually are a way that we can join and decide how these torques from the torque mechanisms affect and explain what we see at the surface in terms of rotation. So historically, V sin I measurements of rotation have been extremely important. Hope I didn't just vaporize somebody with the laser pointer. Be careful with that. And V sin I measurements are still important, especially down at the low mass, but we've had since PP5 a large explosion of data of measurements of the rotation periods. The way rotation periods are measured is photometric monitoring, looking for periodic signals from the dark spots that are rotating in and out of view. And so a part of the increase of this data is due to a large number of ground-based and space-based planet transit searches. because by photometrically monitoring for transits, you automatically get rotation periods. This diagram here, all of these data points represents the approximately 5,400 new rotation period measurements we have just since 2007. And what we're looking at here is the rotation period in a log scale versus mass. And we're plotting masses from about 0.1 to 1.2 solar masses. And each panel is a different cluster of a different age, where in the upper left you have T-Tauri stars of only 1 million years. Age decreases downwards. You have 5 million years here, 150, and then you're really into the main sequence here. And if you look at this for long enough, which some of us have, you'll see a lot of structure in there, but I just want to say right away you see two things. First of all, the initial distribution is very broad. By initial, I mean as soon as the stars are T-Tauri stars and optically visible so that we can measure their rotation periods, we see a broad distribution at all masses that spans almost 2 orders of magnitude, but typically between 1 and 20-day rotation periods. Secondly, you see, if you look at the evolution of the distributions, you see a narrowing for the solar-type stars into a very well-defined narrow sequence of slowly rotating stars. And it's these sequences here which are actually exploited by this technique of gyrochronology to use the rotation rate to measure the ages that works out at those ages. So the nice thing about all this data is we can slice it up now. We have a lot more statistics. That was just since 2007, but that's a factor of a few times more than what we had at PP5. So we have all this data. We can now slice it in narrow mass bins and really start to see what's going on. And this is what we have here. This is just a figure from 2008 and a current figure showing the data now in omega versus, so spin rate versus age in a log plot. And this has been cut from 0.9 to 1.1 solar masses. So there's solar mass stars. And one thing you can see, each vertical collection of points is a single cluster. The symbols represent the lower 25 percentile and upper 90 percentile of the distribution, just to characterize how the distribution itself is evolving. And you can see that we have more data sort of at all ages, but in addition we have now, in particular, very important, we filled in some places where we have gaps, like here at 13 million years. So we now have pretty even sampling in log age space from 1 million years to a gigayear, which is not too shabby. And we're approaching statistically robust samples at each one of these bins. So let's look a little more detail what we've got here. The lines on here are actually model tracks from spin evolution models, which I'll talk about in the third part of the talk. But for now, you can just say these lines kind of guide the eye to trace how the population is varying, or the distribution is varying in time. First thing we notice, as I mentioned, there's a very broad distribution at the very beginning. As soon as we see these stars, there's already a big distribution. Furthermore, as the stars spin up towards the ZAMs, which happens at about 30, 40 million years for a solar mass star, the distribution actually broadens from the initial one, which seems to be because the faster rotators here spin up a little more than the slower rotators do. That spin up is due to the fact that the stars are contracting. Once on the main sequence, we can see these fast rotators spin down, and just kind of empirically, the rate at which they spin down has sort of a half-life of a few 100 million years. They spin down relatively rapidly, main sequence terms, and it's kind of exponential in time. It doesn't have to be exactly that, but an exponential in time implies a torque that depends on the rotation rate to the power of 1, so directly proportional. Also, we note that these stars are rapid rotators and are in the magnetically saturated state of magnetic activity. Now, we also notice, as I noted in the previous plot, that the rotational period distribution converges at about a gigayear, and after that, the stars evolve. This is the sun, by the way. Evolve more or less according to kind of a power law, where the rotation rate depends on the inverse square root of the age. And this was actually, it doesn't have to be exactly that, but this was discovered empirically by Schematic in '72. This particular spin down implies a torque that's proportional to the rotation rate cubed. So a very different dependence on the torque. These slow rotators are in the non-saturated state. So we already have a pretty good hint that the magnetic activity is playing a role in what's going on. We can make similar plots like this all the way down to the to the convective limit of 0.3 solar masses with similar statistics, and we find the same qualitative behavior. The trends are that as you go to lower mass, this spin-down timescale increases continuously as you go to lower masses, and a few other interesting trends, which I don't have time to go into. But what we can do now is look at the next mass spin below the convective limit, or in the convective limit. So these are stars less than 0.3 solar masses. They remain fully convective on the main sequence. And what we see here are a few differences. So, well, some similarities. We see a broad distribution. The mean is a little faster, but we see a broad initial distribution. One thing that's interesting is we see as these spin up to the ZAMs, the distribution doesn't seem to broaden like it did for the higher mass stars. So they both kind of, the fast and slow rotators spin up together. Also, the spin down timescales here for both fast and slow rotators seem to be, again, something like an exponential. So these are, and in fact, all these stars are in the saturated regime. Finally, you see very interestingly, and we have less statistics out here, we certainly need to improve this, but from the data we have, it looks like the distribution, rather than narrowing with age, increases its breadth in age. So you have a very large range of spin-down timescales for these. And this may be related, this is just new suggestions, recent suggestions, may be related to what's seen in both dynamo models and magnetic field observations of these low-mass objects, or low-mass stars, that there might be some kind of a bimodal or a bistability in the magnetic properties that may explain a bifurcation like this. But this is where we need to work that out. So now extending the mass down to substellar mass regime, so 0.08 solar mass and below, to the brown dwarf regime, we have about 200 rotation periods, a little less, for these stars. And here and most of those are on the pre-main sequence. Here we've just binned the data into 3 age bins to show the general trend. This is log period now versus age. The tracks show what you expect with no angular momentum loss. So because brown dwarfs just continue to contract, we expect it'll continue to spin up. And all old brown dwarfs we have measurements for are fast rotators and show maybe evidence for a little bit of spin down, but not much. And again, it's actually consistent with, not that we would expect this, but it's consistent with kind of an increasing spin down time scale all the way extending from stars to brown dwarfs. It's very just suggestive, but it's interesting. So now we have all this phenomenology from the observations. We move on to what are the physical mechanisms that give rise to angular momentum loss or gain in stars. First, I'm going to start with non-accreting stars. So you could think main sequence stars, but it could be non-accreting pre-main sequence stars. So I'm kind of starting backwards and starting at the end of their lives and going backwards because this is a simpler phase. The reason it's simpler is on the main sequence, we already know what the mechanism is for spinning down stars. We've known since the late 50s that it's due to magnetized stellar winds, and we even have a large body of literature on magnetized stellar winds to tell us how the torque depends on all sorts of things. So every model that explains the spin down to date, with up to last year basically, uses a formula which was derived by Qualler in 1988, or something that is different but actually turns out to be equivalent to what I'm going to say here. So everything we know is based on this. This is based on 1D analytic stellar wind theory. And you find that the torque depends most importantly on the magnetic field strength squared times the rotation rate. Because the torque depends on the magnetic field strength, we need to specify what that is to calculate the torque. And so we need a kind of a dynamo relationship, as it's called, which we can get constraints on from activity measurements as well as dynamo models. So this is the one that Qualler used and that most models are using. So with these two pieces, we can actually tell a really nice, elegant story to explain a lot of the phenomenology that I just said. It turns out that the story is mostly a fairy tale, but I'm going to tell you anyway because most of what we know up to last year is based on this story. So the fast rotators, I said, are saturated, and that means that their magnetic properties don't depend on spin rate. So we say alpha is 0, and if you plug that in, you find the torque is proportional to the spin rate directly. It gives you an exponential spin down, perfectly what we were seeing. Secondly, in the non-saturating regime, the slow rotators, you can say alpha or A is something like 1 Might not be exactly 1, but you have b proportional to the rotation rate, and there you get the torque is proportional to omega cubed, which, if you recall, explains this Gumanich style spin down. The problem is, so this is a really great story, but the problem is, and we've known this a long time, but this is just the best that we had. The problem is this torque doesn't depend on the mass loss rate. So this stellar wind spin down doesn't actually even require a wind at all, if you think about it. But so this is interesting, and we knew this wasn't right, but this is all we had. And so this is really not correct, and we need to update it. And I'm not sure if many of you have noticed, but in the last 25 years since this formulation, there have been a few modest increases in computational capabilities and also numerical methods. So what we did with my collaborators, I ran a whole series of simulations of stellar winds where I adopted the same, same assumptions as Koaler, but then allowed the multidimensional MHD simulations to solve for the dynamics self-consistently and run a parameter study and find out how the torque actually depends on the parameters. So for the same assumptions as Koaler, except I'm allowed to relax some because the simulations solve for things that he had to guess. And we find a very different scaling. First of all, you can see the scaling with the magnetic field is very different than b squared. And we finally revealed what is the mass loss rate, the dependence on mass loss rate. So this is pretty new work, and it's just now starting to be put into our understanding. But right away we can see that in order to have this simple story that I told you, we still can have that. But not only does the magnetic field, but also the mass loss rate has to vary, particularly with rotation rates. We're starting to now relate what we see in the spin rates of stars to not only their dynamo properties, but their mass loss properties, which is also exciting. Secondly, I'll mention just at the very end that Reiners and Mohanty have recently pointed out that even this dynamo relationship doesn't fit with observations, and there shouldn't be an R squared there, and that has other interesting implications. So no longer should we be using the Koaler formulation. Since we now have a physical torque that relates, that tells us how torque depends on mass loss, we now, if we want to talk about the spins, we have to care about the mass loss rate and what it is. It's very difficult to measure mass loss rates in low mass stars because the rates are pretty low, which is unfortunate, but I'm encouraged by recent work. I'll highlight the fact that Cranmer and Saar and recently Suzuki have developed a predictive analytic or semi-analytic theory. It's actually an IDL code, which you can download for predicting the mass loss rate of solar-type winds as a function of mass and age. So it comes just in time, actually, to plug right into the simulation torque, coincidentally. And also, there's been a suggestion by these authors that from the observed X-ray flare distributions of different classes of stars, including pre-main sequence and main sequence, you can infer, using solar scaled relationships, mass loss rates from CMEs. There's, of course, a lot of caveats with doing this, but this is very interesting and a promising technique, I think, to keep looking into because we don't have many constraints. Also, I mentioned right at the beginning that the stars don't always possess perfect dipoles, and everything above is related, all of this is related based on a dipole. So it's encouraging that there have been a number of stellar wind models that are starting to take this into account and see how this affects things. So this is clearly the future of this aspect of the field. Now so that's for the non-accreting phase. Turning to the pre-main sequence, again, this distribution or this evolution of the solar mass stars, if I just ask the question, if I take as a given the initial spin rates that are observed and ask, if the stars conserved angular momentum, how would they, what would they look like as they contracted towards the main sequence? And they would follow these red lines, which clearly does not match the data. Just very crudely, it looks like the data do something more like this, where there's some kind of a delay. The distribution doesn't seem to vary that much, as far as we can tell, for a while, and then the stars spin up according to their contraction. So this is really surprising because we know the stars are contracting. In order just to keep a constant rotation rate during that contraction, you actually need to lose angular momentum at a rate that's 6 orders of magnitude stronger or faster than the present-day solar wind. So this requires an extraordinary explanation. In addition, a large fraction of these stars are accreting, and naively we expect when a star accretes from a Keplerian disk, it actually gets spun up even further, which makes the problem worse. But we have known for a number of decades that under certain circumstances, the interaction between a star and a disk can actually extract a net amount from the star under certain circumstances. So this idea has led a while back now to the idea that that's usually called disk locking. And the people that know me will know that I hate the term disk locking even more than Mark Krumholtz hates the term star formation efficiency. So, but that's okay, because it's really the concept behind disk locking, in my mind, which I think is sound, is really just this question or this idea of maybe the star-disk interaction can somehow provide the torques we need. So this is still an open question, and I think it's, I think probably the answer is yes, exactly how we're still working out. So one way you can search for evidence of this is to compare the spin distributions of stars that have disks or have accretion to those that don't. At the time of PP5, people had already been doing this for more than a decade, and some claimed to find it and some didn't. So the results were mostly controversial, in my opinion, at that time. But now I think we have a good handful of observations that are more convincingly show that at least on average, in a statistical sense, you see there's overlap in these populations, and this is one of the best examples, but accreting stars are on average slower rotators than non-accretors. This might not extend down to the very low mass regime. It's still unclear, but the interpretation of this is really unclear, but it does seem that the presence of a disk or accretion does have an influence on the rotational history. So that's encouraging anyway for my next slide, which is to give a quick overview of all of the different ideas we have for how the star-disk interaction may result in spin down or may solve this problem. First of all, this is just a cartoon of the things that work in the inner part of an accretion disk where there is a star, magnetic field. Under certain circumstances, it truncates the disk, and you have accretion flow channeled onto the star. And the star and the disk both have winds, and there's an interface region kind of between the open field line of the star and the open field lines of the disk, which is also interesting. There are models that don't require a magnetic interaction, but that use just different properties of the disk itself. But those usually are only important for removing angular momentum from the star when the star is rotating very close to breakup. So these aren't a good explanation for slow rotators, which we would like. The oldest magnetic model comes from Gaussian-Lamb. So the Gaussian-Lamb model holds that these magnetic field lines that are connecting the star and the disk actually can spin down the star. And I think since PP5, it's become fairly broadly recognized that, at least in the Gaussian-Lamb framework, there's not enough magnetic flux actually connecting in general to solve the problem. So this has kind of fallen out of favor, except in the case of very low accretion rates or very fast spins, you enter into what's known as a propeller regime. This could work for those certain circumstances, but it's still not clear whether that represents the large population of stars for several million years. So we don't know. Second model I'll mention is the X-wind model, which actually avoids this problem of flux by assuming that a large fraction of the stellar magnetic field is actually pinched and trapped at the X point, which is the co-rotation radius. And furthermore, that there's a wind from the X point, which is just like disk winds, which you heard from in the last talk, a nice overview. So we have a disk wind launch, but it's from a narrow region, and that wind extracts all the angular momentum of the accreting material so that the star actually receives no net torque on it. This is the only model that is actually formulated in terms of the amount of magnetic flux participating in the accretion flow instead of the surface magnetic field strength. And that idea that it's the flux in the accretion flow that's important actually has observational support. And I point you to this paper to get more details on that. So that's in the plus column there. All these ideas are controversial, but I'm not going into all the pluses and minuses. So the next I'll talk about is the accretion-powered stellar wind. At PP5, Ralph Pudritz and myself actually presented this as a poster, and it was this cartoon, really. And at this point, it was just a scenario. It was just an idea that, a very simple idea, is just that, well, okay, there's these open field lines here. Maybe there's a wind along there that carries enough angular momentum away to solve the problem. I already told you we need an extraordinary solution, so this requires a very massive wind, an extraordinary wind, and so the only way to power a wind like this, so the amount of mass loss rate you need is something like, it depends on parameters, but something like 10% of the accretion rate. So in order to drive a wind like this, the star can't do it by itself. You need accretion power. So it's just an idea. But since then, this has seen a lot of, there's been a lot of activity on this model, both on a lot of fronts. So it's seen a tremendous amount of development, and now it's really developed into a predictive real theory, I think, not just a cartoon. Finally, there have been a large number of numerical simulations, almost entirely carried out by Marina Romanova and her group, studying a whole host of phenomena that are very interesting things in this star-disk interaction. But I'll just point out from my perspective of the torque on the star, I think the most interesting thing that's to come out is from the recent paper of Zani and Ferrara, and it's actually related to also something that Marina has seen in her simulations, which has been dubbed magnetospheric ejections, or conical winds by Marina. What we see is that this interface region, under certain circumstances, can be very important. That certain circumstances which may actually be present in these systems, you have the magnetic field lines which are connecting the star, and the disk can periodically open up and eject plasma and then reconnect, and this happens repeatedly, and you get kind of a conical wind on average, but you get magnetospheric ejections. And this idea here, Zani and Ferrara actually showed convincingly that this has some properties of all the other models. There's kind of a wind, there's a wind here which is kind of coming from the disk, but also kind of the star. But this is, so it's taking angular momentum from both. But this is, they've convincingly showed this is a distinct mechanism from these others. So just summary, first of all, I think the most important thing to say regarding the accretion phase angular momentum evolution, we still are not sure what is the fundamental mechanism for spinning down the stars or responsible for that. We have there's been a tremendous amount of great theory work. We're moving in the right direction to be answering that question, but the reason I reviewed so many mechanisms is because all of these are still under consideration. I've already mentioned a key thing since PP5 is accretion-powered stellar winds is still a promising idea and received a lot of attention and development. There's a new mechanism that's identified of this magnetospheric ejections. That's exciting. Also, again, magnetic fields are non-dipolar. Most models still using dipoles, but it's encouraging that now we have had some work, including the generalization by Subbu Mohanty and Frank Xu of the X-wind to include non-dipolar fields. So we need to see all the other models starting to do this as well. Oh, I need to also mention, this isn't really theory, well, it's interface between theory and observation, but a good way to discriminate between these is with high-resolution spectroscopy, because we have to probe things on stellar and even substellar radii scales, and we want the kinematics, so especially coupled with radiative transfer. So these works here are actually encouraging, and we've got a lot of insight into the details of does the wind flow from right here or right over here? That's what we want to know. That's what we need to know. Finally, moving on to the models, where we can take these physical torque mechanisms and just say, if that's the torque, what does it look like on a long time scale? How does it change the rotation rate of the star? The main point here is that the mechanisms that I discussed in the previous part are all dynamical mechanisms. They really just show you what the state of a star is and what the torque is during a snapshot in its lifetime. Those models are very complex, and we can only say what happens during a snapshot in time. If we want to evolve the star for gigayears, which we do, or even for a megayear, we need to use 1D simplified spin evolution models. The goal is, of course, to reproduce the observations. And so these always start with a 1D stellar evolution model in order to know how the structure and moment of inertia of the star evolves, and at the same time solve the angular momentum equation for the star, which requires that we specify what the torques are. As I mentioned, until last year, all models are using this older Kowalar prescription. And for stellar winds, during the accretion phase, almost all models don't treat this at all physically. They assume a constant rotation rate for some amount of time and then start solving the angular momentum equation, which is usually called disk locking, but I like to call it we just don't know what's going on here yet phase. Because it might not be due to this. We don't know what it's due to. Anyway, the next thing we need, since the torques act on the surface of the star, is a way to understand how the angular momentum is distributed throughout the interior. The simplest thing to do is choose a solid body rotating star, which is appropriate for a convection zone or a fully convective star. Often models are using a two-zone model where the radiation zone and the convection zone each are assumed to rotate as a solid body, but not necessarily at the same rate, so they can decouple. And then there's a coupling timescale for the transmission of angular momentum between the two. And then there are more, I'll mention a little briefly, there are more sophisticated models under development that are doing this on every mass shell within the star, so more physically. So these spin evolution models are actually, I showed you observational plots of the rotational evolution, and the tracks on those already were these models. So a lot of the phenomenology that I described in the observations of how things are spinning down and spinning up in time come from and were discovered by applying these kind of evolution models to the data. So I'm not going to reiterate all of those conclusions, but I will focus on this one, which I've, I think, shown you now 5 times. You should remember it. It was shown yesterday, too. I'll focus on this and some results that I haven't mentioned. So what you see here first is that they assume the initial rotation is the initial observed rotation. This is that we just don't know what's going on here yet phase of constant rotation, and at this point they turn on, at some point after a few million years, which depends on which track you're looking at, the angular momentum equation is solved. Then you see this spin up from contraction. The stellar winds are on here, but it's just they're not strong enough to counteract that contraction. And then the other things which I've told you, you can see the tracks fit. So this model is the first one to use the new torque formulation derived from simulations. So this torque depends on the mass loss rate, which means the authors have had to specify what is the mass loss rate, and they use this Cranmer-Sarr relationship. And lo and behold, the good news is they fit the data pretty well. The great news is, details aside, the great news is that actually for the first time, we're now able to relate the observations of the spins as a function of time, not only to the magnetic activity properties of a star, but also to the mass loss rates. And so we're actually developing a more coherent and self-consistent, physically self-consistent picture of stellar evolution and bringing in more types of observations into play in a coherent fashion. And this is where I think we need to go. Secondly, this is a two-zone model where the core and envelope can rotate at different rates. The dotted lines here are the rotation rate of the core, and the solid lines are the surface, which is what you see, which is why those match the points. And in order to make the fit this good, they've tuned the coupling timescale so that the slow rotators actually need a longer coupling timescale than the fast rotators. You see there's a lot of differential rotation at the ZAMs, but it's actually larger for these slow rotators. And if this is true, we don't know what this means. It says something about the internal transport and may have implications for the mixing and therefore burning of lithium and things. So that's an interesting result. We don't know exactly what it means. Finally, this is my penultimate slide here. I think that the future of this field really needs to see more development of these spin evolution models to include more physics, and to be more self-consistent, and to connect with more types of observations. And I think this is justified now by the data, as well as great advances in the theory for the torques, that we can start to really think about doing this very, very soon. And there's a lot of work already happening in this direction in bits and pieces I just want to highlight. First of all, I mentioned it sort of in passing, but there are a number of works now that are solving the internal angular momentum transport and exploring a number of different mechanisms for this in the radiation zones of stars. This is still in an exploration phase of understanding the physics and the transport mechanisms, but this is clearly the future of spin evolution models. Secondly, since PP5, there were a few before, but since PP5, I think that myself and collaborators are the only people who have run a spin evolution model during the accretion phase that includes the physics of the accretion phase, so includes torques and actually solves an angular momentum equation. And I'm not saying it was excellent work per se, it's exploratory work. We were actually exploring the accretion-powered stellar wind scenario in this case, but the point being that if you look at the timescales, what we were trying to do here and were able to do with accretion-powered stellar winds with certain parameters is explain the initial distribution that's seen. And then we don't have data points on here. This is 10 days rotation at 1,000,000 years. And the point here is that if you look at the track, look at the timescale, in order to explain the initial condition, you have to actually solve the evolution in the embedded phase. So it's difficult, we have fewer constraints, but actually this is a way to probe, or at least look for a self-consistent picture of star formation that also can be informed by the rotation period distributions. So we need to see a lot more of this. And I mentioned in the past, but I'll go into detail a little more here, Reiners and Mohanty have pointed out that the dynamo prescription used by Koala and used in most of the models to date adopted something that didn't quite match up with the observations, in particular just this radius squared part. And then when they put that into the torque formula, their own torque formula, they get a strong dependence on the radius and mass. The point here is that this model is the first they've attempted to actually solve for the evolution of the stars of all different masses at the same time, including these very low mass stars. So they took this initial observed distribution and evolved them according to their model. Their model is the black points, and the stars are the observed points at the Hyades in red. And you can see at least that they get the broad trend of the narrow distribution of slow rotating solar mass stars and a population of fast rotating very low mass. There's obviously details still to work out, but this is promising work to try to explain this all in a coherent model. Rather than read this, I'll just put up the last 2 pages of our review article, and when you're watching this at home on YouTube, you can pause it and read it in detail. Thank you very much.
Okay. So it's time for discussion. Okay.
A question about the X-wind model. I get a bit confused. I thought that there was growing evidence for the presence of dust in the winds, which is basically inconsistent with the X-wind model. So where am I wrong?
It's hard for me to tell you where you're wrong. So yes, I mean, we could definitely get into a lot of esoteric debates about X-wind and the other models. I mean, you're probably right that that's at odds, but the X-wind doesn't preclude that there maybe is a wind also from further out in the disk. I don't know, I'm just thinking on my feet, but I don't think that necessarily just rules out the X-wind all by itself, but it is interesting evidence.
Okay, so decide.
Okay, Gong Xingli from Max Planck Institute for Radio Astronomy. And I have a very basic question, because as a child I was told that the sun somehow changes direction of magnetic field after a given period, and will that change the evolution of the rotation for your protostars?
Yes, it does. So that's a very good question. The models for the torque assume a steady, constant magnetic field, at least over a few dynamical times, which is true. But the point is the sun's magnetic field is cyclic, and so are other sun-like stars. And the question of whether it affects the angular momentum loss, the answer is yes. In fact, one of the papers by Pinto et al. I cited actually did this. And but the cycle of the solar cycle is 22 years. And the spin-down timescale of the sun is gigayears, or even if we take a young star, it's megayears. So we really take the torque averaged over the cycle, and that's fine. So we hope that the simulations are representative of how the torque is averaged over the cycle. Somebody's done the torque along the cycle, but we haven't seen whether that scales the same way. It probably does, but that's future work to be done. Good point.
Thanks.
Okay, upstairs.
Hi, I'm Elizabeth Newton from CFA. I was wondering if you could comment on the observations that you think would be most important for constraining the models, especially at the low mass end.
Well, for the low mass end, for the spin evolution models, or the For the low mass end, we really need, well, we need more statistics in general, but we need rotation period measurements, especially at the field age, so at older ages, and hopefully be able to put them to know their ages more precisely. Those ages were determined by whether they were thick disk or thin disk, and so there's a lot of uncertainties associated with that. Was your question related to the rotational period measurements? Yeah, okay.
Rob Jeffries. Many of the observational data sets actually only contain rotation periods for a small fraction of the populations that they're claiming to measure the rotation distributions of. Do you think that could be a problem?
Could be. Yeah, so I think though that, for example, one way to answer that, so that the point is just that we only measure, you photometrically monitor a whole field of stars, but you can only measure periods for a subset. And the question is whether the ones that are not observed are systematically slower or faster rotators or something. So one way to address this is actually by comparing with V sin I's, because that's an independent way. And usually where this is done, where there's large numbers, there's no difference between the V sin I distributions and the rotation period. So that's one way to answer the question. But it's not clear that that's completely ruled out. I think that we can be comfortable with that. I think Jérôme Bouvier is comfortable with this, so maybe you can talk with him more about it. But it is a good caveat to bring up.
Yeah, I think I would be more concerned for the older clusters, actually, where sometimes that fraction is as low as 10%, and where you can't really measure V sin I's very well.
Yeah, especially where the fraction is lower, yes. Okay.
Okay,
thank you.
This side.
Morbidelli. As you know, hot Jupiters pile up at an orbital period of 3 days, and the usual justification is that that's the resonance between the orbital period and the rotation of the star. But your diagrams don't show any preferential 3-day rotation period. There is a huge dispersion of over an order of magnitude, I would say. So much broader than the dispersion of orbital periods of hot Jupiters. So can you comment on that?
You're saying that the hot Jupiters pile up, I'm sorry, I'm not an expert. The hot Jupiters are piling up at a location, the argument is that they're piling up at the orbit of the same rotation period of the star, at the co-rotation radius.
Yes.
Yeah, well, that seems inconsistent with the spin distributions. It depends when do they reach that? And do we know, I guess we might know something about the observational, or the trends with rotation period of stars with planets. I think that the stars with planets preferentially, although the numbers are small, are rotating a little bit faster than stars without. So there might be something there. I don't have an answer for you, but that's a very interesting point of contact, I think.
Okay, so upstairs.
Yeah, that goes somewhere in the same direction. I'm Markus Nilbach from the MPRA here in Heidelberg. What you've shown us is mostly dedicated to stars that are in isolation. But is there something that changes everything when you look at multiple systems or even young, dense clusters? But because then tidal interaction might play a role. Is that something important?
That's a very good question, and reminds me, I forgot to make a comment about that. It's true, we've been focusing on single star mechanisms, but the reason for that is just we want to, at least at first, understand the broad distributions. And in order for tidal interactions to happen, the separation is very small, and this can be at most just a few % of the overall sample. In fact, in some of those distributions, you do see a few rapidly rotating stars, which probably are these close binaries. So I do think those are very interesting to study and can probably teach us a lot. But to explain the bulk of the distribution, if you have an orbital separation of, half an AU or something, the stars' winds aren't going to know about each other. They'll collide, but the stars, that's all happening outside the Alfvén radii, so the stars themselves don't even know they have a companion with respect to their angular momentum.
Okay, so this side.
Hi, I'm Henri Trio from the MIT. I'm wondering whether the same angular momentum loss that you're having through the wind could also affect the direction in the spin of the star, and whether its spin could change with respect to us.
I think it's sort of from an academic perspective, I think yes, it could. I have to think about this a bit more. So in a sense of a three-dimensional wind with a complex magnetic field, possibly you could have an asymmetric torque. I'm not sure if that's actually true because the wind is always rotating with the star. I have to think about it more, but I don't think it could drastically. And consider that the spin-down timescales are very long. So just to explain the spinning down of the rotation is enough. If you want to change the moment of inertia, or especially significantly, or the angle, it's the same amount of torque to spin the whole thing down. So it's an interesting question. I don't have a good answer for you, but maybe in more 3D models we can actually look to see if the torque can be not aligned with the rotation axis.
Okay. Yeah, here.
Mark Krumholz, UC Santa Cruz. First of all, I want to thank you for acknowledging my hatred of the term transformation efficiency. I wanted to ask you about, so all of your diagrams sort of ended at one solar mass, and stars don't end at one solar mass. So I was wondering if you could just sketch out quickly what is known and what can potentially be learned by thinking about what happens if you go up to, say, 2 or 3 solar masses. What do we know? What could we potentially learn by looking at slightly more massive stars?
Very good question. I'm glad you asked it. So yes, the massive stars do exist, and they're very interesting. The picture changes in a number of ways. So first of all, observationally, most massive stars are rapid rotators and remain that way for most of their lives. I don't think there's a lot of evidence for significant angular momentum loss. Well, okay, I'm not sure, but I think so. I think the cutoff really is at like F2, and you're talking about an A star, right? So maybe. I'm not sure. Second thing is a lot of what I talked about, of course, are magnetic stars, and that magnetic activity also cuts off at about the same time when you lose the convective envelope. The high-mass stars have about 10% of them seem to be magnetically active as B star or BE stars, et cetera, and AP stars. And those actually often do show evidence for spin down. There are groups that are working on massive star winds, and actually in one case have observed in a single star, they're able to measure the period accurately enough. They've seen the period of the star change, and it does seem to match up with the torque simulation, the torque that they get from their wind simulations, which actually scales the same way as mine with the mass loss rate. So it is interesting, and I do think that the future is not only to develop these models for the low mass stars, but we need to do it for all the stars. There will be different physics there.
Okay.
I think you took the question out of my mouth.
Okay.
I mean, I was also going to ask about massive stars and actually more massive stars, up from A stars up, you know, and I don't know, is there any review? I mean, you didn't cover it apparently. So can you tell us something or guide us through these other domains, you know, of spin evolution? In particular, I was interested whether there are any stars, maybe in the regime that you're discussing, which actually show critical rotation. I seem to recall a VLTI observation where a star seemed to be flattened. So there was at least one star, I believe, that looked oblate.
And those are A stars, I believe.
A stars,
yes.
yeah.
So that's right. Yeah, I mean, the higher mass stars, A stars, and much higher, I think generally are rotating a significant fraction of breakup, 30%, and sometimes even 90 or upwards %.
And how does this come about?
By not having angular momentum loss. Because the stars contract on the pre-main sequence. And actually, some of those tracks, if they didn't have angular momentum loss, especially, you remember there's this kind of disk locking initial phase, if those spun up the way I drew with the red line, they would be at breakup. They would actually go past breakup, which means there'd be something kicking in to stop that. But that's the best way to explain rapid rotation is to have not much angular momentum loss. That being said, with high mass stars,
Short comment, please.
okay, high mass stars are rare. It's hard to draw diagrams with that kind of statistics on the rotation rates of high mass stars, although people are working on this. Also, the lifetimes are so short. It may be that high mass stars are spinning down more rapidly than low mass stars, but they just don't live long enough for us to see a change in the rotation.
Roman Rapikov, Princeton. I have a short question about your torque prescription that you derive from your simulations. I'm a bit surprised to see the dependence on, you know, m dot, b, omega, and so on, and not see the dependence on a stellar radius, because I would expect that, you know, b and r cubed should go together, you know, due to the just magnetic moments considerations.
Yeah, thank you for mentioning that. There is a dependence on the mass and the radius. I simply kept that out to not make the equations too big for time, but there is definitely a dependence, and we have worked that out in the simulations. There is one in the Koala formulation as well, but so that's in there, and it's a proportionality in the talk, but there's actually all those quantities are measured out. There's no fudge factors.
Okay, last question.
Scott Wolk, SAO. I wanted to follow up on the comment about planets, and that is we've done some work, and there's some posters upstairs, where we do see evidence that the close-in planets are in fact spinning up their host stars. And in fact, what it means in a Protostars and Planets group is that the gyrochronology you're trying to do is muddled up, because the planet itself is making the star look a little bit younger. And those are posters by Poppenhager and Piliteri.
That's a good caveat. So they can spin it up by tidal interactions, but also by modifying the stellar wind. I think there's some works studying this. Okay, thank you.
Okay, so please thank all the speakers in the afternoon again.